All right, it is 2025, October, what is it, 7th? It's October 7th. Let me check this real quick. Yeah, October 7th, and it is approximately 1:56 p.m. And we're continuing where we left off with the problems for chapter 4. So let's go 4-4. More recurrence examples. So we have give asymptotically tight upper and lower bounds. For T of n in each of the following recurrences. And we are told to justify our answers, which we always do anyway, but yeah. T of n is equal to 5t of n over 3 plus n log n. That's the first one here. Okay, so let me start off and say, intuitively, when a fixed fraction of, so we're gonna take a look at a whole bunch of different sort of things here, but I'll just say as intuition for all that we're going to be looking at in this problem, where a fixed fraction of n appears, we use the master or Acrobasi theorem. When the decrement is by a constant, for example, n-1, n-2, we enroll in sum. So borderline terms like n over log n yield an extra log of n factor via the continuous master theorem. For one of the parts on here, we'll divide by n after the m is equal to log of n change of variables to get a simple have the argument add 1 recurrence. And you'll see what I mean by that here in a moment. Whenever we get there, it'll make itself rather apparent. But for now, let's just go through these part by part, starting with 1 here. So for 1, master theorem with a is equal to 5, b is equal to 3. So n to the log base 3 of 5 is roughly equal to n to the 1.464. Now, since f of n is equal to n log n, which is equal to big O of n to the log base 3 of 5 minus epsilon for some epsilon greater than 0, case 1 applies. And we'll look at how exactly it applies here after I just erase this and continue to write and talk on it, speak of it. So, because case 1 applies, we have t of n is equal to theta of n to the log base 3 of 5. So there we have the tight upper and lower bounds for t of n, in this case, n to the log base 3 of 5. Now let's go on to the next part here. So part 2, t of n is equal to 3 times t of n over 3 plus n divided by log of n. So here here p is equal to log base 3 of 3, which is equal to 1. And by Akrabazi, or continuous master theorem, we have T of n is equal to theta of n times open parentheses 1 plus the integral from 1 to n of u divided by log of u, close parentheses, open parentheses, u divided by log of u, over u squared du, close parentheses, which is equal to theta of n log of n. So T of n is equal to theta of n log of n. All right, and that's it for the second part. So now let's move on to the third part. So for the third part, T of n is equal to 8 times T of n divided by 2 plus n cubed times the square root of n. All right, so n to the log base 2 of 8 is equal to n cubed, and f of n is equal to n to the 3.5, which is equal to big omega of n to the 3 plus epsilon. Now, regularity. Eight times f of n over 2 is equal to 8 times n over 2. Oh, sorry. 8 times open parentheses n over 2, close parentheses, to the power 3.5. And this is in fact equal to, open parentheses, 8 divided by 2 to the power 3.5, close parentheses, times n to the 3.5, which is in fact less than c times n to the 3.5 for c less than 1. And so we have here case 3, which yields us T of n is equal to theta of n to the 7 divided by 2 for part 3, and that's it for part 3. Let's move on to part 4 now. So for part 4, we have T of n is equal to 2t of n divided by 2 minus 2 plus n divided by 2. The negative 2 in this case is a lower order perturbation, is a lower order perturbation. And what can we say about that insofar as Akrabazi is concerned? Well, we can say, okay, we know Akrabazi handles g of n is equal to n over 2 minus 2, and the balance exponent solves 2 times open parentheses 1 divided by 2 close parentheses to the power of p, which is equal to 1, which implies that p is equal to 1. All right, we're going to have to erase the board and pick this up here in a moment. one of the disadvantages of writing on a smaller board, right, is you have to, if you have big handwriting, you have to erase frequently, a lot more frequently than if you had like a big dry erase board. But so we say with f of n equal to theta of n, case 2 gives t of n is equal to theta of n to the log of n. All right, so let's move on to part 5 here. So for part 5, t of n is equal to 2 times t of n divided by 2 plus n divided by log of n. Now, p is equal to log base 2 of 2, which is equal to 1. By the continuous master theorem, with border case k is equal to -1, we have that t of n is equal to theta of n times log of n, right? On to part 6. T of n is equal to t of n divided by 2 plus t of n divided by 4 plus t of n divided by 8 plus n. Now rigorously, so Akra Bazi with a sub 1 being equal to 1 and b sub 1 being equal to any element of the set containing 2, 4, and 8, and only those. So p solves open parentheses 1/2 close parentheses to the power p plus open parentheses 1 divided by 4 close parentheses to the p plus open parentheses 1 divided by 8 close parentheses p to the power p, which is equal to 1. Now if we let x equal 2 to the negative p, then x plus x squared plus x to the power 3 equals 1, whose root is x roughly equal to 0.543689, implies p is equal to the log base 2 of 1 over x, which is roughly equal to 0.879. Okay, and we're going to need more board space. So let me just get to that. So using AB, t of n is equal to theta of n to the p, open parentheses 1 plus the integral from 1 to n of u over u to the p plus 1 du, close parentheses, which is equal to theta of np dot n to the, well, multiplied by n to the 1 minus p, close, which is equal to theta of n. So yes, that's part 6 out of the way. Now let's move on to part 7. So for part 7, t of n is equal to t of n minus 1 plus 1 divided by n. Now, rigorously speaking, we can just unroll this, like I mentioned earlier, to get t of n is equal to t of 1 plus the summation k is equal to 2 to m of log of k, which is equal to theta of log of n factorial, which is equal to theta of n log n. So t of n is equal to theta of n log n. Okay? No, sorry. It's just log n. It's just log n. I think I messed up somewhere over here. Yeah, this is not right. I was thinking of the next part, but we're focusing on this part. So t of n is equal to t of 1 plus the summation k is equal to 2 to n of 1 over k. Sorry. Yeah, that was supposed to be 1 over k, because 1 over n, which is equal to theta of log n. So t of n is equal to log of n, is equal to theta of log of n. Okay, and that does it for part 7. So t of n in this case is equal to t of n minus 1 plus log of n. So rigorously, well, unroll to get t of n is equal to, here we go, t of 1 plus the summation from k is equal to 2 to n of log of k, which is equal to theta of log of n factorial, which is equal to theta of n log n, and this is by Stirling approximation, right? So t of n is equal to theta of n log n, right? Okay, now let's move on to part 9. For part 9, we have t of n is equal to t of n minus 2 plus 1 over log of n. So that's what we have for part 9. Let's unroll for about n divided by 2 terms to get t of n is equal to t of theta of 1 plus the sum from j is equal to 0 to the floor function of n divided by 2 minus 1 of 1 over log of n minus 2 j. Well, then what do we get there? Well, this is equal to theta of m roughly equal to n divided by 2 to n of 1 over log of m, and this is actually equal to theta of n divided by log n, which is what we want. And that is it for part 9. Now let's move on to part 10. For part 10, we have t of n is equal to the square root of n times t of square root of n plus n. Now, intuitively, we just change the variables, change variables to m is equal to log of n and normalize by 2 to the m, right? So, more rigorously, let's say, let s of m equal t of 2 to the m, then s of m is equal to 2 to the m divided by 2 times s of m divided by 2 plus 2 to the m. And let's divide by 2 to the m and define u of m to equal s of m divided by 2 to the m, such that we have u of m is equal to u of m divided by 2 plus 1. Well, then what can we say about this? As I erase this board, well, we can say depth in this case is theta of log of m, so u of m is equal to theta of log of m, and so t of n is equal to s log of n, which is equal to 2 to the log of n times theta of log of n, which is equal to theta of n times log of n. So for part A in this case, well, let me just say this. So we went through here, we got various cases that matched up to the intuition, and I could, write them all down in one row, but I'm just going to sort of leave it at that and proceed to 4-5, which is on Fibonacci numbers. So this problem develops properties of the Fibonacci numbers, which are defined by recurrence so 3.31 on page 69, which depending on your edition might not be true, but well, in which case, what are you doing here if you don't have the same edition? But anyway, we'll explore the technique of generating function or formal power series, which is interesting that this one uses script f, but that's fine, as script f of 7 is equal to the sum from I is equal to 0 to infinity of f sub I z to the power I, which is equal to 0 plus z squared plus 2z to the cubed plus 3z to the power 4 plus on and on and on. And I'm going to erase this so I can write more on what this problem is stating. So this is where f sub I is the ith Fibonacci number. We have to show that script f of z is equal to z plus z times script f of z plus z squared of script f of z. And second part, we have to show that f of z is equal to z over 1 minus z squared which is equal to 1 over the square root of 5 times open parentheses 1 over 1 minus phi times z minus 1 over 1 minus conjugate of phi times z, so phi hat minus z, where phi is the golden ratio, and phi hat is its conjugate. And for part 3, we have show that f script of z is equal to z over 1 minus z squared, which is equal to 1 over the square root of 5 times open parentheses 1 over 1 minus phi of z phi times z minus 1 over 1 minus, nope, I'm accidentally resetting. Part 3 isn't that. Part 3 is show that f of z is equal to summation from I is equal to 0 to infinity of 1 over the square root of 5 times open parentheses phi to the I minus phi hat to the I close parentheses times z to the I. And it says specifically here you may use without proof the generating function version of the summation k equals 0 to infinity of x to the k, which is equal to 1 divided by open parentheses 1 minus x. Okay, now let's move on to part 4. Use part 3, which by the way, I'm gonna keep saying this, but it's like I'm putting this in terms of numbers, so 1, 2, 3, 4. It kind of makes it easier. I haven't found like an easier way to just put the parts without doing this. Like in LaTeX, I can just sort of use an enumerated list, and I can put like each of these as items for those of you that know, right? And there's probably a way where I could just do this via alphabet, but I'm just choosing not to for now. I refuse. So use part 3 to show that f sub I is equal to phi to the power I divided by square root of 5 for I greater than 0. Rounded, yeah, that's an important part. Rounded to the nearest integer. And we're given a hint here, which is observe that the absolute value of the conjugate of phi is less than 1. Okay? And now for part 5, we have prove that f sub I plus 2 is greater than or equal to theta to the I for I greater than or equal to 0. So pack the Fibonacci recurrence f sub I is equal to, so intuitively is what I'm saying here, pack the Fibonacci recurrence f sub I is equal to f sub I minus 1 plus f sub I minus 2 into object script f of z is equal to the summation of f sub I times z to the power I. Now shifting indices multiples by z one step or z squared 2 steps, so the recurrence becomes a simple algebraic identity in z. Now solving for script f of z gives a rational function. Factoring its denominator by the roots x squared is equal to x plus 1, namely by phi and phi hat, yields a partial fraction form whose geometric series expansions give Benet's formula and the nearest integer rule. So the inequality in part 5 there follows from the fact that phi satisfies phi squared is equal to phi plus 1, and Fibonacci numbers satisfy the same linear recurrence. So now we can begin to look at this a bit more rigorously and just test our gumption against that. So let's see. So script f of z is equal to z plus z. This is what we're wanting to look at. Z times script f of z plus z squared script f of z. That's what we're wanting to look at. Now, using f sub 0 is equal to 0, f sub 1 is equal to 1, and f sub I is equal to f sub I minus 1 plus f sub I minus 2 for I greater than or equal to 2. F of z, script f of z is equal to the summation from I, over positive I. So I greater than, non-zero non-negative I. There we go. That's the one. I greater than or equal to 0 of f sub I times z to the power I, which is equal to f sub 0 plus f sub 1 times z plus the summation I is greater than or equal to 2 of f sub I minus 1 plus f sub I minus 2 close parentheses times z to the power I, which is equal to z plus the summation over I greater than or equal to 2 of f sub I minus 1 times z to the I plus the summation I is greater than or equal to 2 of f sub I minus 2 to the z, times z to the I. Now let's reorganize the shifts. Okay, so reorganizing the shifts, let's say reorganize, let's say recognize the shifts. Recognize shifts. So what I mean by this is we have the summation of over I being greater than or equal to 2 of f sub I minus 1 times z to the I is equal to z times the summation over j being, supposed to be greater than or equal to 1 over f sub j times z to the j well, that's equal to z times script f of z. So the summation over I greater than or equal to 2 of f sub I minus 2 times z to the I is equal to z squared. Well, this is more of me saying this other part, so I should really just put these together, shouldn't I? Yeah, so is equal to z squared times the summation from k greater than or equal to 0 of f sub k times z to the k, which is equal to z squared script f of z. So script f of z is equal to z plus z times script f of z plus z squared script f of z. Okay? And therein we have first part nailed. Now let's go on to the second part, part 2. So for part 2, which I'll use A, B, and all that interchangeably. So closed form and factorization is what we're looking at here. Now from part 1, or from, well, let's call this 2 actually. Let's not start using letters now, even though in my notes I messed up. But from part 1, f of z, so script f of z of 1 minus z squared is equal to z. That implies script f of z is equal to z over 1 minus z squared. Now let's let phi equal 1 plus the square root of 5 over 2, and phi hat be equal to 1 minus the square root of 5 over 2 be the roots of x squared minus x minus 1 equal to 0, then 1 minus z squared is equal to, open parentheses, 1 minus phi times z, close parentheses, open parentheses, 1 minus phi hat times z, close parentheses. So I'm going to erase here in 5, 4, 3, 2, 1. And let me just get to this. So partial fractions. Give z over 1 minus z squared is equal to a over 1 minus phi times z plus b over 1 minus phi hat times z. And if we solve for a and b, by clearing denominators, what we get is the following. If I can get there. We have that z is equal to a times, open parentheses, 1 minus phi hat times z, close parentheses, plus b times, open parentheses, 1 minus phi times z, close parentheses, which is equal to, open parentheses, a plus b, close parentheses, minus, open parentheses, phi hat times a plus phi times b, close parentheses, times z. Now let's go here and we'll say, okay, let's match coefficients. Matching coefficients. A plus b is equal to 0, and negative, open parentheses, phi hat a plus phi times b is equal to 1. So with b is equal to negative a, we get negative open parentheses phi hat minus phi close parentheses a is equal to 1. So a is equal to 1 over phi minus phi hat, which is equal to 1 over the square root of 5, and b is equal to negative 1 over the square root of 5. Okay, so now let's go and let's go ahead and try and finish this off with what we have. So we can say, therefore, script f of z is equal to 1 over the square root of 5 times open parentheses 1 over 1 minus phi times z minus 1 over 1 minus phi hat times z. And that is what we needed for that second part. Now let's move on to the third part, which gets into series expansion. Now using 1 divided by 1 minus alpha z, which is equal to sum over non-negative I of open parentheses alpha times z close parentheses to the I as formal power series, as a formal power series. We have that script f of z is equal to 1 over the square root of 5 times the sum over non-negative I of open parentheses phi to the I minus phi hat to the I close parentheses times z to the I. And that's all we need for that. Now let's move on to part 4, which we're going to be looking at the nearest integer rule. Sort of like an unofficial rule, but I mean, all rules are kind of unofficial until they have real backing of force behind them in a way, but let's put that aside for now and just say part 4, nearest integer rule. So comparing coefficients of z to the power I in part 3 yields Benet's formula such that f sub I is equal to phi to the power I minus phi hat to the power I over the square root of 5 for I greater than or equal to 0, so non-negative I. Okay. Now, since the absolute value of the conjugate phi hat is less than 1, we have phi hat to the power I is also less than 1. And the absolute value of that, I mean to say, and in fact, the absolute value of phi hat to the power I over the square root of 5 is less than or equal to 1 over 5 consequently, right? So, which is less than 1/2. This is for I being greater than or equal to 1. Okay? Now what more can we say on this? Well, so with all that in mind, we can say, so f sub I is equal to phi to the I over the square root of 5 plus an error of magnitude which is less than 1/2. So for I greater than 0, f sub I is equal to phi to the power I divided by the square root of 5, rounded to the nearest integer. So that's it for part 4. Now let's move on to part 5, where we go over the inequality. Well, we'll be more specific on that here in a moment, but the specific inequality in this case, that being the f sub I plus 2 being greater than or equal to phi to the I for I greater than or equal to 1, right? So for part 5 here, f sub I plus 2 greater than or equal to phi to the I for I being greater than or equal to 0. So we prove by induction. Using f sub k plus 2, I mean to say, is equal to f sub k plus 1 plus f sub k, and phi squared is equal to phi plus 1. Now, base I is equal to 0, such that we have the base case, right? So f sub 2 is equal to 1 is greater than or equal to phi to the power 0, which is equal to 1. In this case, equal to, right? So choosing base case, which is kind of trivial, is equal to 1. F sub 3 is equal to 2, which is greater than or equal to, in this case, greater than phi, which is roughly equal to 1.618, and it goes on and on. But now, moving on to the inductive step, let's have an inductive hypothesis. Let's assume f sub k plus 1 is greater than or equal to phi to the k minus 1, and f sub k is greater than or equal to phi to the k minus 1. True for k is greater than or equal to 0, right? So what then can we say? Well, 5, 4, 3, 2, 1, erase. Okay. So we can then say then f sub k plus 2 is equal to f sub k plus 1 plus f sub k, and this is in fact greater than or equal to phi to the k minus 1 plus phi to the k minus 2, and that this is actually equal to phi to the k minus 2 times open parentheses phi plus 1 close parentheses, which is equal to phi to the k minus 2 times phi squared, which is equal to phi to the power k. So f sub I plus 2 is greater than or equal to phi to the power I for all I greater than or equal to 0. Thus completes what we're looking for, right? So we are good to go for problem 4-5. Now we can move on to 4-6, which is fairly long. Okay, so which is fine, but we'll just call it off for now, and we'll pick up with the last two of this set and conclude our multiple parts segment on, well, our multiple parts on chapter 4 problems. But that is it for now.